Cool. So yeah, welcome back everyone. Last week we discussed, we did some review of secure implementation techniques in Rust. And this week we're going to be going over chapters 9 and 10 on randomness and primes. So I will say that we're now getting into a more mathematically advanced section of the book. And frankly, I don't think the cryptography engineering textbook does entire justice to some of the sort of mathematical implications that we kind of need to handle things like the Diffie-Hellman assumption and prime generation and RSA and all that. And I would say there are a couple of resources that I would direct you to. The first is that I think this is the maybe the best introductory mathematical cryptography book that oh gosh, it all just disappeared. This is probably the go-to reference that I would use for learning mathematical cryptography, and we'll discuss that a little bit over the course of this. Okay, my window manager seems to be having some issues. This is probably the go-to resource that I would refer everyone to for catching up with mathematical cryptography. In particular, the sections that might be worth discussing or might be worth looking into this week as homework. We'll be covering basically in the cryptography engineering textbook, I think the equivalent of roughly chapter 2.3 and maybe a couple of sections from chapter 1 are presented, and then we kind of jump straight to primality testing in 3.4 in chapter, what is that, 10? 10. So if you wanted a more mathematically complete background on the topics that we'll be discussing this week, I would strongly recommend this book. You can find it in the course notes for this week. We might dive into it a bit at the end of the section. So yeah, let's wander into the book here. So starting with talking about randomness here. So yeah, I think the randomness chapter is reasonably something that can be taken with kind of a light pass. A good portion of the chapter is mostly devoted to discussing the Fortuna random number generator. And random number generators aren't really something that you very often poke. They're kind of important, but not necessarily something that you often think about when dealing with cryptography, only that you should be using a secure cryptographically secure RNG, or a CSRNG is the usual acronym there. So if you see a CSPRNG, or cryptographically secure pseudo-random number generator, that's what that means. And that is in contrast to the random number generator algorithms that are often more efficient. Like I think the meme is that the Mersenne twister has been used many times for generating secure primes when the algorithm isn't the algorithm is predictable as opposed to I think I mentioned this last week. There are two ways for a thing to be often described as random. It is either unpredictable, which is what we actually want for cryptography, or uncorrelated, where number 1 and number 2 in the sequence are not correlated directly to one another. And so both of those are often called random in practice out in the wild, but cryptographers generally care about the unpredictability as opposed to the uncorrelatedness, or at least we care about both, I think. I think unpredictability implies uncorrelatedness. So yeah, getting into chapter here. Basically, the premise for randomness is that we want to obtain this uncorrelated and unpredictable sequence of numbers. And the way we can do that is we can take some randomness that exists out in the world. And we usually measure randomness in entropy. So the entropy of a system can be measured either by jitter that happens naturally in the system, that when your operating system is running, you can actually measure random statistical variation in the disk. But you can also measure random variation in the user input motions. So common examples of this include mouse movements, keyboard presses, and I think the chapter discusses that software will generate 1 to 2 bytes of random data from the timing of a single keystroke. I haven't actually seen that substantiated anywhere. I seem to have observed that most software that I've seen has obtained somewhere between 1 to 3 bits of randomness is what I've seen in the past. But I wouldn't say that the randomness generated by random keyboard presses or timing in keyboard presses and mouse movements is particularly it's neither low nor high, but we don't really need that much randomness, because usually the way we use randomness is that we seed a random number generator, where the random number generator is producing some sequence of uncorrelated numbers, uncorrelated and unpredictable numbers based on the initial seed, which is generated by usually somewhere on the order of 256 bits of randomness. So we only really need 256 bits of randomness to seed our random number generator. And if we need, say, on the order of 16 kilobytes of random data before we need to reseed the generator, usually that's plenty of time to generate more entropy. So a kind of key point about entropy is that if you have multiple sources of entropy, entropy is when you combine entropy in ways that are commonly used. Like, for instance, I think towards the end of this chapter we introduce hashing 2 streams of entropy together. Combining 2 streams of entropy should be non-reductive on entropy, on the total amount of bits of entropy that you have. What that kind of means is that if you have the entropy stream 1, which is generated by an honest party, and entropy stream 2, which is generated by a dishonest party, the dishonest party should not be able to reduce the total entropy in the combination of those 2 streams. And the way this breaks down is that if party 2 can actually react to party 1's entropy, and this is the adversary that waits and reacts to what they see, sometimes called an adaptive adversary. Then the adversary often can say, okay, now that I've seen your entropy, I'm going to quickly try to come up with, say, 1,000 different ways that I could generate entropy, such that I'll pick the 1 out of 1,000 that's the most advantageous to me. So a reactive adversary can break that assumption, where they can generate their supposed random sequence to their own advantage. We generally assume that our adversary, so this is, so the general property of like a pseudo-random number generator, the highlighted passage on the right here, just says that we assume that our adversary knows the algorithm to generate the random data. And in the model that I just presented, the adversary might even be an active participant in contributing to the entropy pool. So the main goal here is that we want to prevent the adversary from being able to arbitrarily construct the random stream that they want. So the usual answer for that is that we need to choose a random number generation sequence that's unpredictable given some seed. And the natural sort of like primitive that we usually lean on for actually constructing a random number generator is often a block cipher. And that should make intuitive sense if you stop to think about it for a second. We want a keyed stream of random bits. That's just a stream cipher or a block cipher in stream mode. And to switch over to looking at some code here, or the cha-cha stream cipher. So the cha-cha stream cipher is pretty simple, and if you're using the rand library in Rust, you're probably using the cha-cha rand block cipher, or the cha-cha rand block cipher in stream mode. to obtain your randomness. And the way this basically works, and it's a very elegant to specify block cipher. We don't even need to get into the, let's see, here we go. Yeah, so the cha-cha round basically it's a very simple set of operations for four elements A, B, C, and D. There is a quarter round updating A, B, C, and D by some bit additions and XORs and bit rotations, which is pretty much what you would expect for a block cipher. It's just going to scramble the bits somehow. This is the way they scramble the bits, and they calculate that it's secure to various attacks. And so they apply the quarter round a couple of times, naturally 4, or I think it's either 4 or 8. And then they do a second operation by doing some operations on this matrix. Or actually, I think I lied. They say that the quarter round gets applied to this matrix along some of the elements in the matrix. So I think it says so the first column of the matrix, then the second column of the matrix, then the third column of the matrix, then the fourth column of the matrix get applied the quarter round. This is all here. And they run through 8 operations of the quarter round. And the 8 operations constitute 1 execution of the cha-cha stream cipher. I think I heard someone speaking up in the chat. Was there a question? All right.
I think it was just an unmuted.
Yeah, might be that. Thanks for confirmation. So that's basically all there is to the cha-cha stream cipher. This paper is 6 pages, and now we're at the end, which I find that somewhat delightful. That you write a paper, you write 6 pages, you have 2 references, and you call it a day. So that means that this is a reasonably easy to implement stream cipher, and there are ways that it can be optimized by doing some sophisticated techniques using, for instance, SIMD intrinsics, which I don't think we're going to get too much into today, but I will just say that when we're doing cryptography, we're often looking for ways to accelerate the cryptography because we expect it to be called quite a bit. SIMD stands for single instruction multiple data, where you apply a single assembly instruction to multiple parts of your data in parallel. So in this instance, you could apply the quarter round function to multiple parts of your data at the same time. So it's a way to do parallelism if you know that you're going to apply a single instruction to multiple parts of your data simultaneously. It's a way to parallelize that operation and speed up the execution. So we will see that in this implementation, or let's see, where am I at? So this is from cha-cha used in rand cha-cha, the Rust implementation of the default random number generator. We see that as specified in the, let me get rid of this and screen split. As specified in the paper, we have, oh good, experiencing bug. That's excellent. All right, I guess we're not going to see that. Really? Okay, well that works. So the on the right here, we see that we have, as specified in quarter round down here, we specify some quarter rounds, and then they loop through the application of the quarter round operation to the rounds. So I think they specify first the operations up here, and then they second might specify, actually I'm not sure what's entirely going on down there. But this is the implementation of the permutation function here in the cha-cha rand library, which I'll share in the Discord right now in case you want to look at that further. I suppose it might be worth mentioning the inline, the call to inline here. So if this is another example of, similar to SIMD, there are compiler suggestions that you can make, like inline a piece of code that make code execution more efficient. And realistically, the only way to know for certain whether a suggestion to inline this particular piece of code, the only way to know that it's certainly going to accelerate runtime is to repeatedly benchmark on different architectures. The other way is, if you are a bit of an assembly wizard, you can anticipate that if by reading the compiled assembly instructions, whether or not the operation would be efficient. But I would say that I'm certainly not an assembly wizard, so the way that I would test whether an inline call here would actually work would be just benchmarking everywhere. But in general, if you see that the generated assembly is shorter, that doesn't necessarily mean it's more efficient, but it might mean that. So, and what inline means here is that anytime, maybe I should explain what inline actually means. Anytime there would be a reference to call this function, permute general, from, say, any other function, like new cha-cha 20, for instance, permute general would not be a pointer to the function stub of permute general, but this function would literally be written into this other function. So the instructions for permute general would be written in line here, as opposed to a pointer to another subroutine. And so that means that if permute general is used in many places throughout the code base, say if permute general is only used in this one particular function here, that means that the code for permute general is not duplicated in the assembly across the rest of the code base. But if it is used other places in the code base, like here and here, we would see the compiled assembly appear multiple times in the compiled binary, meaning that permute general might be performed more efficiently within each of these functions, but the total binary would be larger. And if that doesn't make sense, it's not super important. Inlining is sort of like, in the broad scheme of things, like an optimization feature that you can use, but it only really matters when we're designing or implementing cryptography that's going to be used heavily. And if you're interested more in inlining and SIMD and assembly, then it would be worth looking into compilers in general and compilers in general, and in particular, I think the Rust standard library is looking at, let's go to portable SIMD. The Rust standard library is looking at ways to do portable architecture-specific instructions. This is what portable SIMD means, is that you can declare SIMD execution on different architectures. So there's kind of a lot going on here, and I think there's currently discussion and working group on how to do optimization and assembly, and how to include optimized assembly in your Rust code. So if that's of interest to you, go check that out. Yeah, where were we? Bringing back the let's get rid of that. Yeah, bringing back the book. We've got, so the attacker. Yeah, okay. So then the rest of this chapter from 9.3 onward is I would say somewhat self-indulgent by the authors, in that they mostly spend the rest of the chapter discussing their the RNG that they designed. And you'll notice that if you do take a look at the code that I just shared in the chat about 5 minutes ago, you'll notice that they basically just say, how do we obtain our randomness seed? Well, they don't really care about Fortuna or any other RNG stream. They basically just say, fuck it, use a block cipher. Excuse me. They say, screw it, let's use a block cipher to initialize the generator, and they basically don't have to care about all of the rest of the chapter that the authors discuss. And as far as I'm aware, this is pretty standard now. That you can use a random number generator like Fortuna, but it's a fairly leaky abstraction in that you're basically at the end of the day going to be using a block cipher to do this random number generation anyway. So I would say like maybe skim or skip entirely the section on Fortuna because it's not really that important. More interesting is I think how the let's skip up to. I think more interesting is the question of how the random number generator cycles through, or how often it reseeds the random number generator. And the question there is basically, so if you have 256 bits of randomness, how much does that buy you? Does it buy you 16 kilobytes of random numbers from your RNG, or does it buy you more or less? And so for that, like there is some like interesting, I think, like question of like how secure is it to use one seed to generate n bits of randomness, and that tends to be sort of like an interesting theoretical point. And I think the end of the Fortuna chapter does actually go into that just a little bit. But I would say that in general, when we're talking about implementing a CSP RNG, we're talking about taking a block cipher like Cha-Cha, which I just showed, and turning it into a random number generator with a couple of tweaks for security. And I would encourage you to take a look at that code if you're interested in how a random number generator is implemented. I think the module that I shared is an implementation of Cha-Cha, and then the actual implementation of the random number generator over on top of it in the Rust random repo is actually a fairly thin implementation on top of it. Yeah, actually, it's right here. So they use a macro to declare their random number generator, which I guess I could talk about in a couple of seconds. Since they generate 3 different round lengths for their implementation, they use this macro, but at the end of the day, each of these 8, 12, and 20 round random number generation steps are functionally identical. So when you see Cha-Cha X core, substitute 8, 12, or 20 as you prefer. So basically their implementation is fairly simple in that there are these marker traits that any RNG is expected to obey in Rust. And the only one that's specific to cryptographic RNGs is, of course, just the flag trait crypto RNG. So just to quickly run over what each of these traits mean, that Cha-Cha 8 core or Cha-Cha X core has a block cipher RNG at its core, means that literally that there is a block cipher at the core. And we can see that here in that the API call says, okay, so if we take the implementation of the Cha-Cha block cipher and we want to get some more bits of randomness, then we literally just say, take the Cha-Cha API refill for and fill up the buffer called R. And R in this case is an array64, which I think they use array64. This is at the top here. Array64 is probably used for some SIMD reason that I could get into. I would bet that this is optimization feature so that they can fill this array more efficiently with some specialized instruction set. But in a nutshell, they're just filling up an array with new rounds. Anytime they generate new bits of randomness, they're just calling the block cipher that's seeded with some randomness seed. And they can get that randomness seed in any of the usual ways. Usually we query the operating system for the randomness, and the operating system measures the entropy over the course of usage. And then that's pretty much it. It's basically the entire cipher here is in these lines. So you got a block cipher that generates the random, or generates the sequence. You've got a seed that allows you to initiate the algorithm in the first place, and then you flag it as a crypto RNG. That's everything. We can get down a little bit beneath that. This is the lower level API. The higher level API that we implement on top of that is the Cha-Cha X RNG. So the Cha-Cha X RNG extends the core by saying that it's a block random number generator over the core. And basically we actually implement the fairly similar set of traits here, that it is a seedable RNG, and this basically just wraps the implementation of the core, doing the seedable RNG wrapping, and then we implement one final trait, RNG core, which is the high-level API that you would expect in Rust for using a random number generator. And this is purely just wrapping implementations of that we would expect our block RNG generic over this core to obtain. And that's it. I mean, so this is a very simple implementation of a random number generator. And we win it basically by saying that block RNG is doing some of the heavy lifting here. And block RNG is a type in, I guess they probably import it up here. Block RNG is a type declared in rand core. But it basically is this trait that, or this type that knows what to do given a core random number generator, which is implemented entirely, or a core block cipher, which is implemented entirely in this trait right here. So in summary, and there is a little bit more that goes on down here, but this is mostly just for formatting the output nicely. So you don't need to necessarily pay much attention to the section down here. If you'd like to, you can. So yeah, that's basically it. Implementing block cipher reduces to, in this case, just implementing you need to have the block cipher in the first place to implement your RNG. But it's entirely just implementing a couple of convenient traits in Rust. So that would be how you would implement a block cipher, or a block cipher based RNG if you needed to. So maybe I should stop here and ask if there are any questions on that last chunk. And I do see that there is a question, how do operating systems like Linux and Windows obtain a source of entropy? Yeah, good question. I actually don't know for Windows, but on Linux, I can refer you to this paper. So the Linux random number generator, as far as I understand, and all operating systems fundamentally obtain entropy in a fairly similar way. There's not a whole lot of sources of entropy that a machine can look to, but in general, they're looking for random magnetic field fluctuations on the disk and user input random fluctuations, so like mouse movements and keyboard presses. And it turns out that a little bit of randomness goes a long way in that in the couple of seconds that it takes your machine to boot, there is a sufficient amount of entropy to seed the operating system's random number generating pools, such that there is some cryptography that happens, I think, at the boot stage of the machine. So usually, I think there's, honestly, I forget exactly what I'm referring to here. There's some cryptographic operation that takes place during the boot stage. And apparently there's a sufficient amount of entropy in just random fluctuations on disk such that those operations are still secure, even with that very small amount of disk fluctuation entropy over the course of a few seconds. But to answer your question, or at least try to, I would refer you to this paper, which I'll link in the chat. Or I think if you just search the Linux random number generator revisit it, you'd find it. And then the second question was, the book talks about a number of different sources. Do modern OSs have a pretty standard, well-known method? I mean, if it's the sources of entropy, I think I would lean back on the thing that I just said, which is user input for entropy is one source, random disk fluctuation is the second source. Any other questions before we move on? And feel free to unmute and speak up if you'd prefer to have a question that way. Does inlining help at all with constant time evaluation as a way to defend against side channel attacks? My immediate answer is no. The secondary answer is still no, but if you are looking at the assembly, the generated disassembly, you are more likely. Okay, so the answer is a hard no, but at the point where you're doing inlining, you should probably also be looking at the generated assembly. And sometimes it can be less obvious that the compiler is hiding things from you until you actually do look at the inline assembly. And there are tools to help you do this. Like for instance, valgrind is a well-known tool in the let's see. I'm going to pull up a thing and see if I can find it again. The answer is ctgrind. Valgrind is a well-known profiling tool for your generated assembly from C. And a while ago, I heard that ctgrind could be used with Rust assembly, but I haven't heard basically anything about it since. So I'm a little bit skeptical of this. But there are tools to help you look at the generated assembly as to whether something is constant time. Inlining doesn't help you at all with generating constant time evaluation. The only thing it does is it swaps out stubs for function argument, or stubs for functions as opposed to the literal function body, if that makes sense. Any other questions? Would you mind increasing your font? Right. I always forget to do this. Thanks for the reminder, and feel free to yell at me more frequently if I continually forget about this. Is this? Okay, so this is now, if I make this super big, that doesn't make the other one super big. Go ahead.
For the question, I was wondering if new primitives which are not so block, non-block primitives like Xudo from Ketchak team are going to replace Chacha and other block primitives for random number generation.
What was the first one you said? What is going to replace Chacha?
New primitives which are not non-block primitives, like Xudo from Ketchak team, or maybe something else.
Yeah, honestly, I don't know. I would be curious to know if there's a more efficient or more recent implementation of pseudo-random number generation, but I haven't heard too much about it. And since random number generation tends to be fairly, it is as efficient as the underlying block cipher, I could see that if you had access to a more efficient hash function or block cipher, which we now actually do have access to more efficient hash functions and block ciphers, then it probably would be possible to replace the existing standard tools for random number generation with those other algorithms, or with random sequences based on those other algorithms. But I haven't been paying too much attention to it, so I wouldn't know. Does that help?
Yeah, thank you. Thanks a lot.
All right. Last shot at questions for randomness before we advance to primes. Rhymes with Grimes. And crimes. 2023 has not been a big year for crimes yet. The random trivia bit that I got this year. Elliptic curve pairings are a commonly used primitive in cryptography because they have some very nice features for creating what's called a bilinear pairing over two groups. And none of that needs to mean anything to you, but the entire reason I bring it up is that the inventor of the most commonly used elliptic curve pairing, Andrew Whale, there was a great blog post about elliptic curve pairings recently, and I discovered the quote that Andrew Whale had apparently gone to prison and said that he thought that prison was, I think, a very serious boon for the abstract sciences like mathematics, and that he came up with the premise of elliptic curve pairings while he was in prison. So I was thinking maybe that bodes well for the previous year of activity in cryptocurrency. Any other questions before we move on? All right, let's move on to random numbers. Or not random numbers, let's move on to primes. So yeah, primes. Okay, so this is where things get a little bit more mathematically involved. And if you're just looking to use cryptography, you might not need to care so much about the mathematics of how cryptography works. But if you intend to do cryptography engineering, I really do recommend that the book that I linked in the section here, Crypto Text, Introduction to Mathematical Cryptography, that's a really good resource. I think that in particular, if you read the first 4 chapters and the first half of 5, and maybe the section on signatures and the final section, that would be a very good undergraduate level mathematical background on the sort of long-standing state of cryptography. If you're looking to do something more specific, like work in zero knowledge, it's probably still worth knowing how the rest of cryptography works. And that book would be a very good resource. It covers everything from how we use theorems from probability theory in cryptography to sort of basic premises in complexity theory, all the way up to how elliptic curve pairings work, which is what I just referred to. It has a section on lattices, though I don't think the lattices sections are going to be particularly relevant to folks not working with post-quantum implementations, but they are interesting anyway. I do recommend this link be clicked for folks who are interested in continuing and sort of want a better mathematical background on the primitives of asymmetric cryptography. And I say asymmetric cryptography in particular because symmetric cryptography, a lot of the time it's where asymmetric cryptography is, let's build the cathedral of mathematical security reductions. Symmetric cryptography is, we scrambled it real good, boss. So there's sort of like a bit of a difference in, I think, the expected level of like mathematical sort of treatment in primitives in asymmetric cryptography versus like the primitives in symmetric cryptography, which makes symmetric cryptography a lot easier to talk about, I think, without digging into some of the underlying results and theorems that sort of allow the entire field to exist on principle. And I guess like the most representative example of that is there is a section, I think, somewhere in chapter 4. It's like section, let's see, I think it's, there's a section in chapter 4 on P equals IP, and there's maybe I should link, I just thought to link a post from Quanta, which they make fun. I love it when buttons break. They make Quanta, the sort of pop science and mathematics news site, wrote a great post somewhat recently on different potential universes that we could be living in with respect to unproven results in complexity theory. And what that all means is that cryptography relies on this assumption that what we think is hard is usually non-polynomial time, or harder than polynomial time. But we don't actually have a proof that the non-polynomial time space of problems is not equivalent or is equivalent to the polynomial space time of algorithms. So like an example of that is, just to sort of state it briefly, if we expect that something should take 2 to the n operations, but it turns out we can prove the result of it in only, say, n operations or n squared operations, then that problem is in the category, the complexity theory category. I should avoid the use of the word category to avoid pissing off the category theorists. That problem is in the complexity class of NP complete. We don't actually have a proof that there is a difference between NP and P. And if it turns out that those were the same, a lot of cryptographers would basically say, well, I guess my life work is gone. Because like the entire point of most cryptography papers is to say this problem is difficult for an adversary, or impossible for an adversary running in polynomial time. And if the adversary actually could run in polynomial time because P equals NP hypothetically, then a whole bunch of papers in cryptography would be totally invalidated. Ironically, actually, let's not dig too deep into that. Ironically, the sort of thread of a quantum computer is somewhat analogous to the thread of P equals NP, and that a quantum computer takes a lot of algorithms that would nominally be non-polynomial time and turns them into polynomial time algorithms by using Shor's algorithm usually. And some of you might have caught last month, there was a paper that came out of a couple of universities in China, a lot of authors claiming something that was kind of wacky. They claimed that they could use what was nominally a non-quantum algorithm to break RSA 2048. So the breakdown of their argument here was that they could use this well-known algorithm in cryptography. I think it was Schnorr's algorithm. And Schnorr's algorithm doesn't require a quantum computer to compute. And they said that somehow executing Schnorr's algorithm on a quantum computer would allow them to break RSA 2048. And usually the way these arguments tend to proceed is that there is some significant complexity class reduction where, for instance, not Schnorr, but Shor's algorithm is an algorithm that would allow you to factor a large number in polynomial time, as opposed to the pessimistic non-polynomial or exponential time algorithm that you would be required to use without a quantum computer. So I guess I'm getting a bit off topic here, but the whole premise was that a lot of weird claims get made about quantum cryptography or quantum computing in general. So don't believe everything you see in a paper is maybe the point here. But the takeaway here is that quantum cryptography in some ways can be looked at, or quantum computing can in some ways be looked at the result of saying, well, if P equals NP, then lots of our cryptography breaks, and you can sort of see quantum computing in a similar light. If a algorithm, an adversary can compute something in polynomial time using a quantum algorithm, then a lot of stuff breaks. Though a lot of people seem to be misusing or outright confused about what a quantum adversary can and cannot achieve. So that's side tangent over. Let's talk about primes. The section on primes that I particularly recommend in the book that I just referred. So the chapter 1 is excellent background. It covers some of the topics that we're going to cover that we cover in cryptography engineering. Chapter 2 is a look ahead to chapter 11 and what we'll be talking about there. And chapter 3 is the section where we finally actually talk about what we're talking about today. So the arrangement in cryptography engineering is a bit out of order from the arrangement that you would find in a mathematical introduction. And I don't expect you to be able to skim read a mathematical introduction to cryptography, in that it's a bit more dense and requires a bit more time to understand. But if you do want to understand some of the stuff that we're going to go over today in cryptography engineering, I do recommend it. So divisibility and the primes. We're going to skip over these lemmas here. They're sort of basic premise algebra. If you find that these are new to you, it's worth taking time to go over these proofs. But they aren't the central focus of this lecture today. When we're talking about generating primes, like the classical trivial algorithm is the sieve of Eratosthenes, which basically you just construct a large list of numbers and then cross off the numbers that are divided by some prime and keep counting up until you're happy with your list. And if you say that your list ends at, say, 100, well, there's going to be no prime smaller than the square root of 100 that doesn't. So taking, if I wanted to know if 97 was prime, well, supposing that there was some prime smaller than 97 multiplied by some number larger than I honestly just need a whiteboard at this point to explain this. Basically, the sieve of Eratosthenes, the takeaway here is that this is a trivial algorithm to generate a list of prime numbers, and it's not particularly efficient. The thing that we do want when we're talking about prime numbers is, well, we really want huge prime numbers. And sometimes we want properly big prime numbers, and the sieve of Eratosthenes would mean that we needed to apply a reasonably slow algorithm for generating primes that are on the scale of like anywhere from 80 bits to 1,000 bits. So even if we had a square root time algorithm, if we wanted to generate a 1,000 bit prime and we had a square root algorithm, it would take 500 bits of computation, or it would take on the order of 2 to the 500 computational steps. So obviously that's not going to happen. Since our cryptographic algorithms are usually on the order of 128-bit security, generating a 1,000-bit prime would then be 500-bit security, meaning that you would never finish, and you would never finish very many billions, trillions of times. So we need better algorithms for finding large primes than the sieve of Eratosthenes. And the way we kind of get to those algorithms is that we need the element, the mathematical sort of intuition of groups and finite fields. And the reason that we need this is that we have a particularly useful lemma from groups and finite fields called Fermat's little theorem, as opposed to his last theorem. And Fermat's little theorem is much more useful and interesting than Fermat's last theorem, frankly. In that it gives you a way for understanding in computation modulo some prime. It gives you a way of knowing that any number to the power of p minus 1 over this group or a field is congruent to just 1, or more properly, the identity of the group or field. And if that made no sense, that's fine. But I would encourage you to read this section and try to understand it. And if you feel like you still don't understand it, I would refer you to hit up the section. I think Fermat's little theorem is actually introduced all the way in 1.4 in this book. So I would refer you over there. But the entire piece here that we win is that we have a very convenient and useful result for saying, even in a field that is modulo an arbitrarily large prime, we can prove some result about that field. Namely that if I take n to the power of p minus 1 modulo an arbitrarily large prime, and if that value is equal to 1, then it is potential evidence that P is prime. It's not confirmation that P is prime, but it's evidence towards P being prime. And so, like, maybe to nail that home, I think this would honestly be better if I think maybe next week I start figuring out how to get a whiteboard up so that I can have a little bit better prepared notes here. The basic premise here is that you want to collect pieces of probabilistic evidence towards P being prime. And so this is exactly what we're doing with the Fermat's little theorem that I just mentioned. If we take arbitrary value n to the power of p minus 1, oh, there's a way to do chat comments. That's interesting. If we take an arbitrary n to the p minus 1, and the value obtained is 1, then we win evidence towards p's being prime. And if we say develop some probability that if n equal p to the n minus 1 equals 1, how many bits of evidence do we get towards p being prime? And then we can say if we want 80 bits of evidence that p is prime, then we repeat that algorithm for a different n some number of times until we're particularly satisfied that p is prime, and then we can use p as a prime. And there are some particular things that we need out of primes for different algorithms like RSA or Diffie-Hellman or whatever we're using the prime for. And those are specific to the particular algorithms, but in general, the kinds of primes that we typically want are primes that have very few factors of p minus 1. Because a lot of the time there are ways to work out solutions to simultaneous modular arithmetic equations using something called the Chinese remainder theorem if p minus 1 has many factors, in particular if it has many small factors. That's not particularly important to know, but the main thing to take away there is that usually we want to, when we're selecting a potential prime p, we're looking for primes of the form, for a smaller prime q, we want to multiply q times 2 and add 1. And then if p is prime, then we have a safe prime, since the factors of p minus 1 are only q and 2. And if that made no sense, don't worry too much about it. But take a look at Sophie Miller primes, which I guess I forgot to put in the notes, which I guess I'll update. I'll just grab this right here. I'm going to say Sophie Germain primes, that was it. I'll link Sophie Germain primes in the notes, which I seem to have forgotten to do. Sophie Germain primes and I think it's called safe prime. Sophie Germain primes would be q in the previous example, and then 2p minus 1. I guess they're calling p. Yeah, all right. So what I called q, they're calling p. The number p is the Sophie Germain prime, and the safe prime 2p plus 1. If that is also prime, then it is referred to as a safe prime. And okay, let's move on a little bit here. Yeah. The other main, I think, thing to take out of this section that's worth noting is that you should aim to be comfortable with the extended Euclidean algorithm. The extended Euclidean algorithm is used pretty much universally in cryptography because it obtains the result that it's easy to compute inverses in a group. And just as a heads up, it is inconvenient for me to obtain the chat for... Oh, no, I got it. All right. It looks like someone has been suggesting drawing software. That might be helpful. I'll look at that for next section. The extended Euclidean algorithm is used to obtain the result that it's easy to compute inverses, logarithmic time, in a group, which allows us to do all sorts of things in cryptography, but mostly it says that it's easy to work in groups and compute inverses using the extended Euclidean algorithm, which is very important for our usual field of operation, which is prime fields. So it's worth understanding and taking time to understand out of this section the extended Euclidean algorithm, which I think is also covered in it's either in chapter 1.3 or chapter 1.4. I think Fermat's little theorem is treated in 1.5. So I guess, like, to reiterate, this is a very good introduction to a lot of the things that we're going to treat at a very high level in cryptography engineering are treated with a bit more formality in chapter 1 of an Introduction to Mathematical Cryptography. And basically, the result of the GCD algorithm, or the result of the extended Euclidean algorithm, is that we win that a lot of computation over finite fields is actually very easy, and it allows us to treat working in finite fields relatively conveniently. But most importantly, it suggests to us like there's one particularly hard problem that we'll talk about next week, and that's the Diffie-Hellman or discrete log problem. If computing inverses is easy, that does not imply that the algorithm discussed in chapter 11 is also easy. That is, computing n to the x equals g, where x is unknown and n and g are known. Obtaining x is hard. Is the discrete log problem. Actually the rest of this chapter is reasonably... I guess the other thing to take out of this chapter is the Rabin-Miller test. The Rabin-Miller test, which is postponed in the other book until section 3.4 and 3.5, or no, 3.4, is treated here. And I frankly wouldn't expect the majority of the class to feel like they understand Rabin-Miller based on the presentation given here. But it is a very important result because this is actually how we check whether an arbitrarily large number is prime. So if you would like to understand the Rabin-Miller test, feel free to ask questions in the chat. But I don't think the treatment in this chapter is sufficient to actually understand the Rabin-Miller test. So do try to understand it, but know that I think that the cryptography engineering textbook is sort of falling down a bit here, and that I don't think they actually treat the test very well in how they describe it. And with that, I think we might switch over to answering questions before we wrap up here. I guess it's already 10:44. So yeah, any questions? Okay, so I can see that there is some discussion going on in the chat. Inlining. FBI Elegek says that the sieve of Eratosthenes is actually a very efficient algorithm for finding primes in a given range. It's a very efficient algorithm for finding small primes. It's a very inefficient algorithm for checking whether an arbitrarily large number is prime. And usually we actually want to do the latter of those two things. Further, it's a reasonably efficient, and that is square root of n time. It's not quite logarithmic, but I don't think there is a logarithmic algorithm. So yeah, it is a reasonably efficient algorithm for finding small primes, but not checking if a large number, an arbitrarily large number, is prime. So maybe that was me misspeaking. Square root of n time is particularly good for most algorithms, but not for algorithms that we want to use to obtain, say, or to obtain 1,000-bit primes. So maybe that's the clarification that was needed. Sophie Germain were on the notes. Oh, maybe I botched. The no deterministic algorithm for efficient. Okay. Yeah. Any other questions? I think that was it. Are large primes used for well-known crypto curves simply Miller-Rabin tested? Nope. For obtaining arbitrarily large primes, it's basically Rabin-Miller to prove that they're a prime, and that's a probabilistic proof that they're a prime. We might get roughly on the order of 2 to the 80, or we might get 80 bits of evidence before we conclude that P is probably prime. Part of me would be uneasy thinking that we only know... right. Yeah. This is exactly it. Is that the thing that you just brought up is sort of like one of the core things that you grapple with in cryptography, and that we often only we're very confident, but never entirely confident that something is true. So 2 to the 80, for instance, is like a ridiculously large number. It means that we have 1 in the chance of, so if a million is 2 to the 20, and a trillion is 2 to the 40, then it's 1 in 1 trillion to the 1 trillion to the 1 trillionth power, or 1 over that. That 2 to the 80 chance doesn't actually hold. So 2 to the 80 is pretty strong evidence that something is true. But at the end of the day, it is only just strong evidence. So R large prime numbers are R large primes used for well-known crypto curves Miller-Robin tested. Yeah, so that is it. We actually, if the prime needed to be of the size that I talked about earlier, even just a 2 to the 128 bit prime, if our best algorithm was square root time for finding whether or not, let's say p to the 128, p is on the order of 2 to the 128, we still need to do 2 to the 64 bits of computation. And I think that sounds like we could probably do it in a period of days or weeks, depending on how strong our computing hardware was. But it would certainly not be a trivial computation. So yeah, in general, we use specifically probabilistic algorithms to obtain evidence about primes that are much larger than that, because there's literally nothing better that we can do. And interestingly, the zero knowledge proofs also operate on a similar probabilistic assumption, that it's possible to cheat a zero knowledge proof, but we generate our security parameters such that it is overwhelmingly unlikely. I don't know if that made sense, but that is to say, probabilistic certainty is something that we often rely on in cryptography when we prove security assumptions, in that we want something to be overwhelmingly unlikely, but oftentimes that is actually a massive improvement over we can't do it at all.